In previous sections, we already saw how we could take spectra of, say, stars or galaxies to infer a lot of their properties. Specifically for galaxies, we can actually obtain a lot of information for their spectra. For example, if we take a spectrum and we see emission lines, we'll be able to study the ionization state of the gas in those galaxies. For example, the presence of some strong lines that have high ionization potentials means, or typically implies, the presence of massive stars, recent star formation, for example. Now, these lines are also really useful because if you measure them and compare with the rest frame wavelength, you can determine their redshift. And with a simple cosmological model, you can transform a redshift into a luminosity distance. This allows you to, for example, transform a line, and by measuring its flux and also its observed wavelength, to calculate the luminosity distance, and therefore to get, say, a luminosity. The other thing you can do, because we've calibrated some of these relations, is transform something like a luminosity, in this case H alpha, in terms of the star formation rate for a galaxy as a whole. On the other hand, we've seen that if we take spectra, we can actually look at the presence of different elements, and with some modeling and understanding, for example, what is the temperature, or technically what is the electron temperature, we can actually figure out what is the abundance of elements, for example. Typically in emission lines, we'll be looking at the abundance of elements in the gas, while in absorption, we may be able to trace the abundance of elements in the stars that are present in galaxies. We've also seen how we can go from magnitudes to, say, the total number of stars, and specifically if we have some understanding or make some assumptions about the IMF, and also use our knowledge of stellar formation and evolution, we can actually infer, say, the total amount of stars in a galaxy, and we can actually convert, if we know what is the ratio between mass and luminosity, when we observe a certain luminosity, we can convert it to mass. There are many other things that we can observe. For example, in the gas phase of galaxies, we've seen how CO is really useful to trace molecular gas. We can also observe neutral hydrogen through the 21 centimeter line, and all of those observations can be combined to, for example, estimate the amount of fuel that might be used for star formation and to calculate things we call gas fractions, essentially the ratio between how much mass there is in gas and how much mass there is in total. And this total may contain dark matter, or it may just refer to stellar mass. And for example, the ratio between gas mass and stellar mass tells you something about the potential to form more stars in the future. On top of just measuring specific lines, by exploring the Doppler effect with adaptive optics, a technique that we covered in section 6, we can actually obtain a lot of resolved detailed information about galaxies, even those that are very, very far away. These techniques essentially allow us to measure the dynamics of these very early galaxies. You can see an example here where we'll be able to tell that the galaxy is rotating. That is because the light from a specific line is all redshifted on this side, and it's blue shifted on this side. And we can use modeling to actually infer the rotation of this galaxy. We can, of course, take a picture of the galaxy. This is how it would look like. And also, if we point at galaxies which are even further away, they will look much more like this. And we can even trace the amounts of heavy elements, for example, nitrogen, in relation to hydrogen as a function of distance from the center to the outside, leading to the conclusion that, at least for most galaxies, they are typically more metal rich towards the center, and they become more metal poor towards the outskirts. And therefore, it implies that the galaxies, most of them, they grow inside out. One of the really big revolutions for studying galaxies that are really far away in a resolved way have been essentially the creation, deployment, and usage of some of the best instruments on large telescopes that allow us to conduct these sorts of observations for many galaxies at the same time. And this is just a real example of some 8 galaxies that existed something like 7 billion years ago, where we can very easily detect their dynamics and specifically measure rotation and even rotation curves. And you'll see that for most of these, you can see them flattening out with evidence of presence of dark matter in these galaxies as well, even though we're seeing them as they were 7 billion years ago. By obtaining state-of-the-art observations at the peak activity of galaxies, that's at the redshift of 2, roughly 11 billion years ago, we've been able to find a lot about how galaxies, some of them that have evolved into look something like our own, how they looked and how they evolved from then onwards. For example, we know from measuring how much gas there was in those galaxies versus how much stars that those early galaxies were very, very gas rich. Typical galaxies now will have a fraction of gas to total, sometimes just a few percent. Galaxies back then had something like more than 50% gas fractions. It meant that most of the mass was actually in the form of gas and not stars. Very likely as a consequence of those very high gas fractions, a lot of fuel, those galaxies were able to form stars at much higher rates, and therefore they were also experiencing something like 10 to 30 times higher supernova rates, leading to the ejection and release of a lot of energy, making these galaxies much less stable as, for example, our own Milky Way. We also know by looking at some of these galaxies, and you have examples here taken with a Hubble Space Telescope, that a lot of them were very dusty. And a lot of these red colors have to do with dust and not the presence of very old stars. We also know that many of these galaxies, like this one, were quite poor in terms of metals or heavy elements, but many other galaxies, even 11 billion years ago, already contain as many heavy elements as our sun, for example. And some galaxies were even supersolar. They had even more heavy elements than we can find on the sun and on Earth. A very important question, though, is what happens to these galaxies that were so active, so full of gas, and experiencing insane amounts of supernova to transform them into the local galaxies that we see today?